internet, on the Facebook, recorded forever.
Yeah.
Facebook is going to have it forever.
Yeah.
Well, I think the best, this one, I think is the best. Pocket to put it on. There is a clamp. And here, I'm going to put it here. I think it's good.
Okay.
And there is this two microphones I'm going to give to plateia em inglês, esqueci. The people.
Yeah.
Eu esqueci o que é plateia. Well, if someone asks some question before lifting the hand, it is not going to be recorded.
Yeah, so then I should repeat the question?
Yes, if you synthesize it and repeat a version of the question, it's better.
Yeah.
Because else people is going to the recording and transmission is going to
Miss that bit.
be without the
Question.
the question.
Yeah.
I think that's it.
Yeah, thank you very much.
Any problem, you can gesticulate to me. I'm going to be there.
Okay, thank you.
Oh, you're welcome. Have a nice presentation.
Thank you. Thanks.
Does it need to press something to start, like, for the microphone? Does it need to press a button?
No, the microphone, I just, it's on
Yeah.
already.
Oh,
Yes.
Yeah, but he hasn't.
Oh, now I hear
He hasn't. Okay.
It's can you hear? Ask if she's.
Can you hear me?
Yes.
Okay, cool. Cool, thanks.
Obrigada.
De nada. Os microfones eu deixo com você.
Pode deixar assim, a professora pode me ajudar?
Tá.
Os dois têm que apertar algum botão?
Eles estão desligados, mas se você quiser, a gente pode já deixar ligado.
Não, é só apertar aqui, né?
Manter pressionado vai ficar verde. Ali. Manter. Já ligou.
E agora para pegar também?
Isso.
Obrigada.
De nada.
Yeah. Yeah.
But did it go for all of the slides?
No,
Okay.
but it'll be fine.
You did it on Windows, right? So it's not going to get.
Yeah.
Okay. I always like to see it like near the corridor, and then right.
But you don't have to be here for that microphone bit, right?
But I think someone is going to come and then I'll just ask them. But I'm going to try it.
Yeah, it doesn't matter.
If not, then whoever is here.
Yeah. It doesn't matter. Inviting people only come in the last few minutes. Like,
Yeah, that might happen.
Oi?
oh,
Nem a professora Rose está aqui?
A professora Rose está de férias essa semana, não sei se ela vai vir.
Ah, ok.
O pessoal está atrasando.
hey,
Eu sou a única não meteorologista aqui.
Everybody's coming back from their lunch,
Mhm.
so I guess they will 5 minutes.
Mhm. Should I start 5 minutes late?
Yeah, start for, just wait.
Yeah, yeah. Yeah, that's fine. Yeah.
People are coming back from lunch. Welcome to Brazil.
That's fine.
Yeah, we're always late.
That's fine.
Shrunk. I don't know. Shrinks. I don't know. Yeah, that's what I know she's coming. Like, she is. She had to come because of the birthday. I forgot the birthday. Today was birthday? Today? No, what? Where you go? Let's go. Yes. I think you should say. That's okay. Okay, could you introduce? Okay, no, because I'm gonna try to get the book, the signature book, because usually Fatima, Professor Fatima does that, but she's in here and I didn't think about getting it, so I'll go and try to fetch it.
Okay. Yep.
But I'm gonna, this is a bit.
Yep. Hi. Good. How are you?
So long.
Yeah, good to see you. Yeah.
Yeah.
Have a nice presentation.
Thanks.
Eu nem sei se eu consigo colocar o vídeo na hora que eu vou fazer da última vez que eu vi o repertório de mais e coisa. Eu não sei se quando soltar aquilo ali não vai ficar. E aí o outro ele trocou a pecinha da própria arte, ele trocou. Bom.
Should I close the door or no?
We'll wait for Livia.
Huh?
We'll wait for Livia.
Okay. Don't worry, it's okay. Like Latin America, we take a little bit. Like we say at 2 o'clock. It's like
Yeah, it's not like.
yeah. Like, everybody's coming. Yeah, everybody's coming.
That's fine. Yep. Yeah, anything's fine.
Okay, let's wait just a minute, okay? She would introduce you.
Okay, yeah, that's fine. Yep. I don't mind. Anything's fine.
Ok, boa tarde a todos. Eu vou introduzir o Dr. Robert Lee, da Universidade de Reading. Ele é PhD em Atmospheric Science, and yes, tenho uma cola aqui. And so he will tell us about his recent research. And I think this is a very important topic, and we have a particular interest because we also research on teleconnections, MJO, and ENSO that affects Brazil area also. So welcome, Robert Lee. Please, you can start now.
Thank you. My work at Reading, I've been working with Steve Warner, who's also at NCAS, National Centre for Atmospheric Science in Reading, with me, and Andrew Charlson-Perez, he's head of Department of Meteorology in Reading, and also Frederick Vietart, he works at ECMWF, which is the European Centre for Medium Range Weather Forecasts, and that's also in Reading. So I'll talk about subseasonal teleconnections from the MJO to the North Atlantic and Europe. However, the MJO has teleconnections which go all the way around the world and to other places, including Brazil. So some of the things that I talk about, there might be equivalent things in the Southern Hemisphere as well. But I haven't researched those. Anyway, so to start with, I'll introduce the Madden-Julian oscillation. So this is the driver of subseasonal predictability that I'm looking at. So the Madden-Julian oscillation is a major fluctuation of tropical weather on weekly to monthly timescales. It's an eastward moving dipole of enhanced and suppressed convection. It gradually moves east and typically takes 30 to 60 days to make one lap of the tropics. And one commonly used index is called the real-time multivariate MJO index, also called the RMM index, and that was by Wheeler and Hendon in 2004. And so this is and that's based on outgoing long-wave radiation, which is shown in the shading here, and then zonal winds at 850 and 200 hectopascals. And so this is just an animation that I've made using ear interim data to show how the MJO progresses east over time. So in the North Atlantic, this is important because we have, it can enhance predictability. So this is a figure from VTAR 2014, and it shows, the improvement in forecast skill over time. So in 2002, the correlation of the NAO at a lead time of 19 to 25 days. It used to be about 0.4, 0.5, and now it's 0.6 to 0.7 in 2001 when this, over this time. And in this figure, they've plotted two separate lines, and those are on days when there was an MJO active and on days where there wasn't an MJO active. So it used to be that when there was no MJO active in the conditions, we had a better forecast skill than when it was active. But then over successive improvements to the model, since 2007-8 onwards, now when there wasn't MJO active, then we actually got a better forecast skill at about 3-4 weeks ahead when there was an MJO active. So it used to be that the MJO was so bad in the model that it used to make the forecasts much worse. But now the MJO is better, and with the teleconnections being better, then we have a better forecast skill. So that's just a motivation for how the predictability from the MJO can impact the North Atlantic circulation. One way to measure the North Atlantic circulation is via something called weather regimes. You could create weather regimes for any part of the world, but for the North Atlantic, we commonly use 4 weather regimes. So these, you can use a clustering algorithm to split the large-scale atmospheric flow into distinct patterns, and these are particularly relevant on subseasonal timescales, so that's 10 to 30 days. Commonly used method is by Michelangeli 95, and this uses a machine learning clustering algorithm, which is just a k-means algorithm. You start with geopotential height at 500 hectopascals, and this is for the Northern Hemisphere winter season, so that's November, January, February, March. Next, from this geopotential height data, you compute EOFs, empirical orthogonal functions. We just need the first 14, and that's just to simplify the data a bit before the machine learning algorithm creates the clusters. So the first EOF is often referred to as the North Atlantic Oscillation. So when we have a dipole between the Azores and Iceland. The second pattern is sometimes called the East Atlantic pattern. That's just a kind of an extension of the jet into Europe and back again. And then, yeah, another 12 more patterns are used, or 12 more EOFs are used there. Just to show that when you use 14 EOFs, you end up using, this accounts for about 85% of the data. Some people, if you're just looking at the NAO on its own, then that would only be using 16.4% of the data. So one advantage of using clusters is that it accounts for more of the data than if you're just talking about the NAO on its own. Then after that, you use the k-means clustering algorithm with 4 clusters, and then it just weights the distances. So for example, the first EOF is strongly relates to the NAO negative and NAO positive clusters. The second one relates to a cluster that's called Atlantic Ridge, and the third one relates to a cluster that's called Scandinavian blocking. The number 4 was picked in the paper. They talk about classifiability and reproducibility, so they just use some tests and find that in the North Atlantic, then 4 is a statistically significant number of clusters that you want, whereas in the North Pacific it's 3, probably, and you could repeat the same process for other parts. Recently, I think some of my colleagues have been looking at North America and have computed similar things for the North American continent as well. So these are the 4 patterns that come out. So we have the NAO regime, NAO positive regime, Atlantic Ridge regime, and Scandinavian blocking regime. So in this one we have a ridge over the North Atlantic, the center of the North Atlantic, and then in this one we have a block over Scandinavia and northern UK. This relates to some surface impacts from each regime. So in the top here we have temperature. So in the NAO negative regime we have a very cold Scandinavian region and also the UK. In NAO positive, we end up with a warm Europe, warm for most of Europe. Similarly, we have reduced winds for much of the UK region and increased winds in NAO positive regime. And in precipitation, the Scandinavian blocking regime results in a very dry for most of Europe, and in NAO negative we end up very wet for Iberia region. So then there was a paper that related by Kosu in 2008 that related the MJO teleconnections, or the MJO to the North Atlantic regimes. So here we have the NAO negative positive Atlantic Ridge and Scandinavian blocking regimes, and then in the rows here we have the MJO, from MJO phase 1 through to MJO phase 8 at the bottom here. And then the for each subplot, it's the relative anomalies of each regime relative to the full climatology. So the main 2 things to note is that after MJO phase, and then the y-axis, the x-axis on each subplot is the lag days from the MJO phase. So at around 5 to 15 days after MJO phase 3, we have increases of up to 60% more occurrence of NAO positive regimes. And after MJO phase 4, it's the same as well. Then we have a little bit of positive anomalies of Atlantic Ridge and Scandinavian blocking after MJO phase 6. And then 10 days after phase 6, 10 days after phase 6, then we have increased anomalies of NAO negative up to about positive 75% after phase 7. 100% anomaly would be a doubling of that regime. So this has been useful for energy traders, energy forecasters, energy companies, and also other businesses which might use subseasonal forecasts, such as the agriculture industry, health industry as well. Because, for example, you have more hospital admissions because this is winter. We have more hospital admissions after NAO negative regime because of cold-related illnesses. So I've just repeated that same analysis, but updating it with the interim data and adding some more years. So now we just have a few more statistically significant anomalies compared to the figure that we just saw, because there's more data going into it. But now we see statistically significant anomalies from MJO phase 1 through to MJO phase 5 for the NAO positive anomaly. And I've also added MJO phase 0 on the top. And phase 0 is just when the MJO is not active, which is about 1/3 of the time. And then we still see small amounts of Atlantic Ridge anomalies after NAO positive and Scandinavian blocking, and then into NAO negative as well. So my analysis just repeats that so far. Here I've just adjusted the y-axis because that will be apparent later. So now I've looked at ENSO conditions for the winter. So I've made an index using the ENSO 3.4 temperatures, and I've just split them into terciles over the 39 winters. So we have 13 winters which are El Niño temperature anomalies, 13 with neutral temperatures, and 13 which are negative for the winter mean. And then this is the sea surface temperature anomalies just plotted. So yeah, clearly we see El Niño, La Niña, and neutral. Next, this is how the MJO animation looks if we subset by the El Niño. So there are some differences. So this is for all winters together, and then when we split by ENSO, there are some bigger differences between El Niño and La Niña. If I wait till it loops around to phase 3, the width here is shorter than the width of the convection or the enhanced and suppressed convection in La Niña years when we look at about phase 3. And that's because of the anomalous Walker circulation that's generated by the El Niño temperatures that tends to squeeze the width, the longitudinal width of the convection in phase 3 in El Niño years, whereas in La Niña years here in phase 3 it's quite extended longitudinally across the equator. So then this has an impact on the teleconnections that are triggered. So first of all, just to describe the statistical anomalies. So before, where we saw anomalies of up to about 50% increase when you look at all years together here. Then when we look at El Niño years on their own, then we have anomalies of up to almost 100%. So that's a doubling of the NAO positive regime during El Niño years. Then we also see a clear increase in Atlantic Ridge and Scandinavian blocking. Often the Atlantic Ridge and Scandinavian blocking are not forced from upstream by the MJO. This just tends to be in situ development, so that's just as the wave breaks in the north, as waves break in the upper troposphere, they often break in a particular way, so as to force particular regimes. So Atlantic Ridge and Scandinavian blocking are more just a consequence of the wave of NAO positive breaking, then they just trigger those regimes. So we term this whole evolution into Atlantic Ridge, Scandinavian blocking, and then into this short spell of NAO negative, all as in situ development in this El Niño subset of years. There's another interesting point to note that so when we look at all years together, we have NAO positive occurring around 30% of the time. In El Niño years, it occurs 33% of the time, so there's a slight shift in the distribution towards NAO positive between the four regimes. Yet when the MJO is not active, which is about 32% of the time in El Niño years, then we have a negative anomaly of about 25%. So we would expect that if the MJO never occurred, then we would expect that we would have less NAO positive during El Niño years. But in fact, we get 3 percentage points more here, and that's mostly due to this NAO positive teleconnection being very strong, slightly shifting the distribution such that we would have more NAO positive days for the whole of the winter in El Niño years, and that's because of the MJO teleconnection that's forcing that. And so this suggests a rectification being possible from the MJO forcing that. Next, looking at neutral years, there's the teleconnection from NAO positive is a lot weaker. There's a lot less significance going on here. Instead, we have the NAO negative teleconnection. So the fact that we see a diagonal pattern, like a diagonal slant between the rows, that's just because the MJO takes about 6 to 7 days to progress from one phase to the next. And so like what's on day 10 here might be on day 4, 5 here. And so this diagonal pattern here indicates that we do have a teleconnection being present, which is forcing ENSO neutral. However, ENSO neutral turns out to just be a kind of combination of El Niño teleconnections and La Niña teleconnections. And I'll talk a bit more about that in a minute. So finally, for the La Niña year teleconnections, we don't see an NAO positive teleconnection at all. So we have sort of climatology amounts of NAO positive. Instead, we see much larger amounts of NAO negative teleconnection of up to 150% anomalies. So that's 2.5 times more frequent amounts of NAO negative. The way that the MJO propagates during La Niña years, because it's more dry in the East Pacific in La Niña years, the MJO signal tends to die out, and so often the days which occur 15 days out here are not the same days as might be here. So where we would expect to see a diagonal pattern going from 8 through 1 and then through to 2, actually we don't see that, but that's partly just due to the way that the method builds up the days here are not quite, the days in phase 8 are not quite the same as days in phase 2. But this is still a real teleconnection, and these increased amounts of NAO negative do happen. We see other sort of random-ish amounts of anomalies of Atlantic Ridge and Scandinavian blocking, but I'm not, I don't think there's any clear teleconnection relating to those. Those tend to be more seemingly random at the moment. So what I've just shown you was based on weather regimes. If you look at the actual just raw Z500 anomalies, you see exactly the same thing. So, for example, in El Niño years after MJO phase 3, we have a clear. So Europe is at the bottom of this polar stereographic plot, and so we have a clear NAO positive regime here, and then similarly down, say in La Niña years after phase 8, then we have a clear NAO negative anomalies here. So even if you didn't bother going through the complicated clustering algorithm, you can still see the same results from the raw geopotential height anomalies. Next, I'll show you some evidence for the dynamical basis for these teleconnections, because so far I've only shown you statistical evidence. So to start with, thinking about jets acting as a Rossby waveguide. And so for this, some of the best evidence is from Hoskins and Ambrisi, from his winter and summer Northern Hemisphere papers, or summer and winter for the Southern Hemisphere. So essentially, when you have a strong jet, then this guides Rossby waves along the jet, and so then they can propagate from one region of the globe to another along the jets. And you can read the paper for more dynamics on that. More recently, it's been shown how different wave numbers that are forced propagate in different ways along the jets. So if we think about a Rossby wave number 2, which is very large in scale globally, so that means like 2 highs and 2 lows going around the globe. This tends to, focusing on the red line here, so Rossby wave number 2 tends to travel in an arc-like pattern. So here, if the anomaly is forced in the Pacific, tropical Pacific, it tends to just travel in an arc-like pattern up to the high latitudes and then back down to the tropics again. Whereas if we have wave numbers, say wave number 4, in this experiment, which is using barotropic Rossby wave theory, in this idealized experiment, Rossby wave 4 tends to instead travel along the jet and go all the way to Europe. So yeah, again, see these 2 papers for more on that. Then the MJO acting as a Rossby wave source. So it turns out that how the position of the MJO can force Rossby waves in a different pattern. So from MJO phase 2, we have, so that's when the MJO is over the Indian Ocean for the active part of or the enhanced convection, and then the suppressed convection is sort of over the eastern side of the maritime continent, sort of Philippines region. So then we have divergent winds traveling northward over the active part, and then divergent winds traveling southward over the suppressed part of the convection. And then when we have the subtropical jet coming over China and then Japan here, this what they call asymmetric dipole forces Rossby waves in a much stronger way compared to, say, if we have MJO phase 4, or 5 as well, which is further east. So the active part of the convection is centered over what they sort of term like a key point in longitude, which they find as 135 degrees east. And so here we have a symmetric dipole rather than asymmetric dipole, and so we only have northerly divergent wind anomalies. And so with the 2, so after phase 2 we have an asymmetric dipole, and so then that's better at forcing Rossby waves than when we have a symmetric dipole, and they're both acting in the same direction. That tends not to force Rossby waves in the same way. So essentially, phases 2, 3, 6, and 7 are better than phases 1, 4, 5, and 8 at forcing Rossby waves. Again, this is so this part here is from a linear barotronic model, and then this part here is just looking at air interim data. And so that is exactly what we see here. So earlier I was talking about how after phase 3, it's coming up here. So here we have quite a longitudinally narrow band of convection when it's in phase 3, and that happens to just be aligned over the right region to strongly force Rossby waves. And then the width of the convection is forcing different Rossby wave numbers. And so here, if we work it out during phase 3, the approximate width is about 3.7 for a Rossby wave number, whereas down in La Niña years, after phase 3 here, this blue part, we see that that's Rossby wave number 2. And so that's why here we have forcing which would tend to travel along the jets, whereas in La Niña years, we tend to have forcing which would just travel in an arc-like pattern over the hemisphere. So then if we look further east, downstream, looking at just geopotential height contours as a Hofmüller plot from day 0 down to day 15 for all years, El Niño years, neutral and La Niña years. Cassou, in his 2008 paper, plotted a figure like this to show the Rossby waves traveling east. This is after MJO phase 3. Whereas we find that in El Niño years, this Rossby wave train is much stronger. And in La Niña years, this Rossby wave train is non-existent. And that's, so then looking at OLR shading here in the color shading, again, this is just frozen on phase 3. So we have a much narrower region of enhanced and suppressed convection in El Niño years compared to La Niña years. It's probably hard to see from there, but there's vectors drawn on, which is the phase-independent wave flux, and then blue line contours are stream function anomalies. And this basically just shows the Rossby waves traveling along the jet. Also, another thing to note is that in El Niño years, the exit of the Pacific jet is further south than in La Niña years, and so then you tend to get a more lined up jet which can guide the Rossby waves further into the North Atlantic, whereas in La Niña years, the Rossby waves tend to just be deposited in the Vancouver kind of west coast of North America and Canada. One other, so I've just talked about a tropospheric mechanism for Rossby waves to travel from the MJO to the North Atlantic region. There's one other pathway, which is the stratosphere. So this is just a random schematic that I've got from NOAA website. So there's the polar vortex, which is high up in the stratosphere over the poles. And when we have a strong polar vortex, well, we can have a strong polar vortex and a weak polar vortex. And we did, me and my supervisor did some work looking at how the stratosphere vortex strength anomalies relate to the weather regimes. And so we have NAO negative, positive Atlantic ridge and Scandinavian blocking here. And we see that when we have a weak vortex, we tend to get more NAO negative regime anomalies being forced. And then when we have a strong vortex, we tend to get more NAO positive and Atlantic ridge being forced. So there's also a relation between the MJO and the stratospheric vortex. So here, this is polar cap temperature at 10 hectopascals in the stratosphere. This is from a paper by Garfinkel et al. In 2012 in JRL. And essentially after MJO phases 7 and 8, so this is time going up the y-axis, and then MJO phases on the x-axis. After MJO phases 7 and 8, we tend to have a warmer stratosphere. And after phases 2 through 6, then we tend to have a cooler stratosphere on sort of short time scales from the MJO. So then I've just replotted that same figure here in top left with the polar cap temperature. But then if we subset that by El Niño years, we tend to find that generally the stratosphere is generally warmer in El Niño years. But in La Niña years, it's generally a bit cooler, but we also have a stronger dependence on the MJO phase. The temperature in the stratosphere is also related to the vortex speed in the stratosphere, just by thermal wind balance. And so in all years, we have a slower vortex after sort of 10 days after after MJO phases 7 and 8, and a faster vortex after phase 3. But then if we split that again by El Nino, we generally have a much slower. So anything that's coloured here is statistically significant in its impact on the troposphere. So on the weather regimes. So here we are much more likely to force NAO negative regime after phase 8 in particular, and more likely to force NAO positive after phases 2 and 3 here. But this is highly significant, and again coming up at about 10 days after phase 8. And so there's a sort of travel timescale for the waves to be forced by the MJO, then to travel up to the troposphere, slow down the vortex, and then come back down from the stratosphere, forcing NAO negative in the troposphere. And so that's why we tend to see from the statistical plots that I was showing you earlier, that's why we tend to see it's about 15 days after phase 8 for this whole teleconnection pathway to take place, so as to force more NAO, like 2.5 times more NAO negative during La Niña years. Next, there's just a bit of time to talk about the eddy-driven jet in the North Atlantic. So there are 3 regimes in the North Atlantic. Tim Willings did a paper in 2010 looking at the eddy-driven jet. So that uses the zonal winds at 850 hectopascals between 0 and 60 west in the North Atlantic. So that's just the ocean part of the North Atlantic. And it found 3 regimes, which are just sort of modal peaks. If we focus on the black dashed line here, and the grey is just the 2 sigma climatology from that. So there's the central regime, which is at about 35 to 40 degrees north. Sorry, southern regime there. Central regime at around 45 degrees north, and a northern regime at about 55 degrees north, which is the sort of northern UK kind of latitude. Next, I can calculate the MJO phase. And so here I've plotted the MJO phase for phase 7, or 10 days after phase 7, in this purple line. And so from the previous, from the statistical analysis, we know that we have more NAO negative. And an NAO negative pattern means that we have anomalous easterlies in the central regime and anomalous westerlies in the southern part of the regime, just from the circulation anomaly from NAO negative. And indeed, we see statistically significant amounts of southern regime winds and statistically fewer amounts of central regime winds. So next, you can also relate the other regimes. So I just said that the NAO negative was related to the southern jet. NAO positive is related to a central jet. Atlantic Ridge and Scandinavian blocking are both related to a northern jet in the North Atlantic. You can then composite this into a Hofmüller plot in a similar way as the contingency tables did that I showed you before. So on the y-axis, we have the jet latitude from 20 degrees north up to 80 degrees north. Then on the x-axis, we have MJO phase, first for climatology, then for no active MJO, and then from 1 through to 8. And then for each subplot, the x-axis is the lag days after the MJO phase. Then we see, so where it's outside of 2 sigma, then I've stippled it in white where it's above, and black where it's below the climatology. So when we look at all years together, we see that the jet is generally in a central regime, then it moves to a northern regime. So it's central regime from phases 1 through 4, then it moves to a northern regime over phase 6, which aligns with the Atlantic Ridge, and then from phases 6 through 8, then we have more amounts of the southern regime. Yeah, so essentially, these are independent metrics looking at weather regimes and jet regimes, but they all show consistent results. Again, if we look at differences between the climatology and the El Niño subsets, we see that we're in the central regime a bit longer for El Niño years, then it moves off to the north, but we see less amounts in the southern regime, particularly early on, and that those closely relate to what we saw from the statistical point of view for the weather regimes. In neutral years, we don't see so much going on in the central regime and northern regime, but we do see more amounts of the southern regime. Again, this is consistent with the statistical point of view for the weather regimes. And then in La Niña years, we have this absence of central regime going along with this absence of NAE positive teleconnections. We see these random Atlantic Ridge and Scandinavian blocking anomalies just showing up there too. And then right at the end, we see more amounts of the southern regime coming in at the end. So to conclude, we see a robust dependence of the teleconnections from the MJO to the North Atlantic, dependent on the ENSO phase. We see more amounts of NAO positive teleconnection in El Niño years, and this pathway is generally via the troposphere. In NAO negative regime, we see more amounts of NAO negative, and we see an absence of NAO positive teleconnection, and this is coming via the stratosphere for the NAO negative teleconnection. In neutral years, we see aspects of both teleconnections coming in. We see that regime progression, so that's like persistence and transitions statistics, which I haven't shown here, but those are all modified when you subset by ENSO, and so in situ development is also much clearer this way. There's also evidence of rectification of the subseasonal teleconnections onto the seasonal mean state. And finally, raw geopotential height plots and eddy-driven jet are in agreement with these teleconnections that you see through the weather regimes. So here's a schematic looking at some of the key parts of this teleconnection, just as a summary. So in El Niño years after MJO phase 3, we see an asymmetric dipole over the Indian Ocean maritime continent region. This forces stronger Rossby wave trains with the jets closer aligned to each other, going all the way into the North Atlantic, triggering anticyclonic wave breaking, which I haven't gone into here, but and then you end up with more NAO positive. Whereas in La Niña years, the convection dipole is much broader, so you have more of a symmetric forcing over this maritime continent region. There are no real Rossby waves forced, and the jets are more separated anyway. And then we have, so in looking at phase 7, we have again no clear coupling with the vortex, the polar vortex, whereas in La Niña years we have the way that the coupling relates deepens a low in the North Pacific. This enhances vertical heat flux, which I didn't really go into, but then it warms the stratosphere, weakens the polar vortex, and then you get downward coupling leading to NAO negative. And then in after MJO phase 3, we have decreased vertical heat flux into the stratosphere, which cools it slightly, and then we have downward coupling forcing more Atlantic Ridge, which was the one anomaly that we did see after MJO phase 3 in La Niña years. So there are some implications of these of this dependence of the teleconnection on the ENSO phase. One minor one, there might be a potential sensitivity to climate change, in particular if there's any change in El Niño, how that interacts with the MJO, the position of the tropospheric jets, how they align, and also how the polar vortex might respond to any climate change. There's implication for subseasonal predictability, and this is the main one that companies are most focused on. So there are interannual variations in subseasonal predictive skill that is possible. For example, if we know that we're in an El Niño year, then we know that the NAO positive regime is more predictable. So we just need to look at what the MJO phase is, and then we know then we can, if any forecasts go for a NAO positive regime, then we can believe them more. This applies to the climate system and also the predictive skill in numerical models. And it stresses the importance for models to get the background state correct in order to represent these teleconnections. But the models also have to have a good enough skill at predicting the MJO, which goes back to that figure that I showed at the beginning, where the MJO used to be predicted poorly, but now it's predicted better. And so that improvement in the MJO prediction then improves the prediction of the general circulation at about 3-4 weeks ahead. Another implication is on, so in the North Atlantic, there's on a seasonal timescale, there's something called the signal to noise paradox. And generally the model, an ensemble mean can be better, gives a much better prediction than any individual ensemble member. And often, so then there's a paradox, and that generally comes from if the model is unable to, like if there's not enough signal coming from the different parts of the atmosphere, then there's too much noise, and so then this generally gives a predictive problem when looking at seasonal timescales. And finally, decadal variability. So if there's a decadal variability in MJO, then this could lead to a decadal variability in the NAO, for example. So just a recent figure that my supervisor Frederick has made. So this is looking at MJO amplitude in the 20C reanalysis. So this is going from 1901 to 1910 and just in 10-year groups through to 2001 to 2010. And in 3 different reanalyses here. And so we see the MJO amplitude was slightly larger in the 1910s. Then in the 1930s, 40s, it dropped off. And then in recent decades, the MJO amplitude has increased. And if you separate that out into individual phases, you see the same sort of thing, where we see a drop-off in the 1930s. This also correlates somewhat with the mean NAO, so whether you have a positive or negative NAO. Again, it was higher in the 1910s and lower in the 30s and 40s, and then it's increased again since then. So it might be that if we have a stronger MJO, we're forcing more positive NAO regimes, and then we're ending up with a mean increase in the NAO index overall. However, this is just a sort of work in progress, and we haven't got too far with this, but this is just a hypothesis of how the MJO could influence distributions between various states in various parts of the world. So to summarize, ENSO modulates the teleconnections from the MJO to the North Atlantic. I've shown this via lead lag compositing to compute anomalies, as well as via analysis of the dynamical mechanisms. This has implications for real-world predictability, model predictability, and also for the biases in the models, potentially climate change, and also potentially rectification onto longer timescales, such as seasonal and even multi-decadal, perhaps. And so this work was published a few weeks ago in GRL. So yeah, thank you for your attention. Any questions?
Okay. Any questions? I have lots of questions, but I will just make one. Is that, are you planning to mirror this investigation to the southern hemisphere?
So I'm not planning to. In my project, we have the next thing we're going to look at is how this teleconnection behaves in the subseasonal models. So that will be the next thing I'll do for my project, because we have certain deliverables and so on. However, I think it would be interesting to look at how it is. One of my colleagues, Regina Rodriguez, who works in the south of Brazil, she published a paper looking at how the MJO affects blocking over the sort of southern Brazil, and yeah, they they find a good teleconnection there. And it might be that ENSO also modifies that MJO teleconnection. So like it would be a very interesting thing to work on, and yeah, I'd love to do that if only I had more time and yeah, funding.
Great, thank you so much.
I have a basic question.
Yeah.
What's the impact on Europe with the NAO positive and negative, and with the coupling with the MJO? Because I don't know.
So this is how the regimes relate to the surface temperatures and also the wind speeds and the precipitation. So when we have an NAO negative regime, then we tend to get cold weather for Scandinavia and the UK region. When we have the NAO positive regime, then we tend to get warmer temperatures over Europe, but this is winter, so it just means mild weather. It's not like you can wear shorts or anything, it's just fewer coats maybe. And then for the wind speeds, we tend to get less winds during NAO negative and more winds during NAO positive. Also less winds during Scandinavian blocking. And there are a lot of wind turbines around the North Sea area, so that's the region of ocean between the UK and Europe. There's a lot of wind turbines there, and so with reduction in wind speed there, then that has implications. Well, we have a big shortfall in electricity, so that's the difference between the generation and the demand. So when it's cold in Europe, everyone puts on their electric heating in some parts of Europe where you have electric heating. And so if you have lower wind speeds, so that's lower generation, and higher demand from the colder temperatures, then that leads to a lot of shortfall in electricity during NAO negative regime. And we have a lot of, like the least shortfall or kind of a lot of surplus of electricity for the NAO positive regime. So actually for the past few days, overnight, electricity prices have been negative. So that means that if you turn on some electricity, the electricity company will pay you to use up energy because they're generating so much from all the wind turbines, and they need people to really use the electricity for anything, and they're not using it so much because it's warmer. So yeah, for the past few nights in the UK, electricity prices have been negative, depending on your tariff overnight. Then there's also relations to the wind, to the precipitation. So in Scandinavian blocking, we have much less rain. So and like more rain during NAO. So yeah, for that Scandinavian blocking, and then more rain during NAO positive. And so water managers have to be careful during this regime, because if your reservoirs are already full, and then you have more rain coming in, then you could get a risk of dam bursts and things like that. So on a subseasonal timescale, if you know that this kind of weather was coming, say 10, 20, 30 days ahead, then you might want to reduce your reservoir levels a little bit in advance before the extra rain came. So this is another use of subseasonal prediction as well.
And this is more important in winter?
Yeah, correct. So one, the MJO is not so active during the summer. Instead it's called the BS-ISO, but in general the MJO is not so active during the summer or Northern Hemisphere summer. Also ENSO tends to be stronger during the Northern Hemisphere winter. So all of these things are generally winter things. However, there probably are teleconnections that come in summer. They just might also have different pathways. Instead of coming, the jets are also weaker as well, so you tend to get fewer raspberry waves guided through the jets. Instead, other pathways might be active, so there might be a pathway through the tropical Atlantic and sort of eastern Pacific, more of a kind of direct pathway that kind of just comes from the, so like it just kind of comes across the Atlantic and then up into Europe in a more direct way rather than all the way from a long way away via the jets. Also the stratospheric coupling is not really active during the summer either. Yeah.
Any more questions? No? So let's thank again Robert Lee.
Thank you. We finished on time. Cool, thanks.